Hi guys, and welcome to this video about the product rule. Apologies that this is going up late again. The main reason for that is I had the whole thing done and then managed to actually delete the whole video, which was very annoying, I can tell you. Okay, and anyway, we're having a look here at the thing called the product rule. Okay, so for the product rule, what we're having a look at is a situation where we have two functions being multiplied together. So let's take a look at maybe an example that currently we won't be able to do, but perhaps sometime in the near future we will be able to. So here we've got an exponential function with a quadratic. Now, yes, you can expand that out. That won't necessarily help you to derive it. So we'd need to know how to derive exponential functions here as well. But let's take maybe an example of something that we could do at the moment. So let's take a cubic function and let's say we're multiplying that with a simple quadratic. Now sure, we could expand this out and derive, and that's a perfectly valid method. But what we're going to have a look at here is keeping the two functions as a product. So here we're multiplying the cubic with this quadratic, and what we're going to do is we're going to call this first function, in this case the 7x cubed function f, and we're multiplying that with another function, and we're going to call that function g. Okay, so how do we derive that situation? So we're going to have a look at a general method of deriving when you've got the product of two functions. Now just a little bit of work on the side here. Okay, if we have a function, now we know that derived function is equal to this, and yes, there would have to be a limit in here as well, but I'm deliberately just leaving that out for the moment because all I want to do is to rearrange the order of some of the terms here. Now if I want to make fx plus h the subject, then would bring h over, giving f dash x times h equal to this right hand side, and then bring the negative fx over to this side. And so would say that fx plus h, what's left here, would equal this, and would be moving the fx over, so it become positive fx. Now a very similar thing for gx, and let's just put that here. If you did exactly the same working, but we're starting with function g dash x, you'd end up with this as an equivalent expression for g of, g, not f, of gx plus h, so it can be replaced with this. So why is that applicable? Well, what we're interested in is the derivative then, and going back to first principles and taking this limit, this h tends to 0 of this function here, would have replacing x with x plus h throughout, take away the original function, and we're all over h. Okay, so how would we proceed? Well, what we're going to do is we're going to replace each of these two parts here with these equivalent expressions, and we'll see why that's a really good thing in a moment. So let's just do the replacement for now. So we've got that in place of fx plus h, and this one in place of gx plus h. My apologies guys, I've still got that cold. Okay, now to proceed here, we're going to do the obvious thing, expand this out. Okay, so two h's would give h squared, and you'd have f dash x times g dash x. And then f dash x times h times gx would be h f dash x. Excuse me, that x is appalling looking. So again, that would be f dash x times gx. So that times that. Now this one times this. Once again, put the h first, and g dash x times fx would be the other parts, and then that times that would be fx times gx. Okay, so that's expanding out that pair of brackets. Take away now our original function, and all of this over h. Okay, so let's cancel the obvious two things which are the same, one positive, one negative. Now notice also that h appears throughout the rest of that top line now, so we can take h out as a common factor, and so let's continue here. Let's take that h out, and we just highlight it in red. And we've got h f dash x times g dash x, and taking h out from this would leave f dash x times gx, and h as a common factor out of that would be g dash x times fx. Okay, and that is all over h. Once again, we have a common factor now of h, so let's cancel that. And now, as we've done with other similar examples and using this first principles method, if we substitute this h as 0 into here, in fact we wouldn't have our limit anymore, would we? So let's get rid of that. We would have this disappearing, and we're left with these two parts here. And what we're left with is known as the product rule. Okay, so we started with the product of two functions, this up here, and now we've got the derivative equal to this, and this, as I just said a moment ago, is known as the product rule. So let's take this example here and let's use the product rule to derive it rather than expanding it out. Okay, so let's make a new page. So we had 7x cubed, and we had x squared, and what was the other bit? 3x minus 2. Okay, so just to emphasize again, this is our function f, our 7x cubed, and we're multiplying that with another function, our quadratic here. So if fx is equal to 7x cubed, the derivative using the shorthand rule would be 21x squared, and a function g is equal to that quadratic, its derivative would be equal to 2x plus 3. Okay, and so coming back to here, what's our derivative? Well, according to the product rule, it's f dash x times gx plus, let's get that right, times gx plus g dash x times fx. Not something you'd write down every time. Okay, but for this, okay, we've got the 21x squared, so let's substitute that in, times our gx plus the derivative of g, which is 2x plus 3, times function f. Okay, and I'm going to stop at this point here. Yes, you could continue and simplify this, and I acknowledge that expanding this out and deriving using the shorthand rule would be much quicker. But for here, we're just trying to practice this thing called a product rule. So this is the initial application of the product rule. Okay, I'm going to stop here and we'll look at some further examples tomorrow. So catch you.